But if you looked at the um, work that you had to do, the pre-lecture stuff, I had a YouTube video for you to watch, I think. And then what was the other one, like Minute Physics or something? I forget who actually put that together. Khan Academy, maybe. Anyway, the course is taking a turn here because it's becoming more mathematical. The assumption now is that pretty much everybody in the class has one full semester of calculus behind their belt and is pretty far into their second semester of calculus as well. And so it's and even in the third semester, let's see, everybody's into their third semester now, right? Because this is a fall semester. Has anybody taken differential equations? Give me a raised hand or something in that if you've taken differential equations yet. And I guess you would have had to somehow test out of, because of AP classes or something like that, Calculus 1 and Calculus 2, if at this point you've already taken differential equations. Anybody? No, I didn't think so. Every now and again, you get somebody who is ahead on their math, but most of you should be planning to take differential equations in the spring semester. And it's probably one of the most important courses of physics major, or somebody who's interested in the physical sciences should be taking. And that's the reason why there wasn't a pre-lecture video from me going through Schrodinger's wave equation and showing you how that works. If you've never taken a course in differential equations, it would be unfair to just, hey, watch this and now you'll know. If you have any questions, though, as I'm going through today, stop me at any time. There's some things obviously that I'm going to be teaching you that your math background doesn't support yet. And so hopefully when you see it in your math courses, it'll make sense. But I think everybody's in multivariable calculus right now, right? Anybody say no to that?
I
Good.
think we're all in the same
Yeah, I think
class.
yeah, so everybody's in multivariable. Differential equation, which is what we're going to be talking about, Schrodinger's wave equation today, is a differential equation. And so what is a differential equation? It's just an equation that has derivatives in it. Go figure. And everybody's taken differential calculus, so they know that. Rather than just having constants and variables, you have constants, variables, and derivatives all in an equation. And a course in differential equations will teach you how to solve those equations. And it's a lot like solving a quadratic equation the first time, where you had to factor it by trial and error. Remember the first time some, I don't know, seventh, eighth grade, maybe a ninth grade teacher had you solving a quadratic equation? It was a guess and check kind of thing. What two numbers add up to be this and multiply together give you this, right? And you had to go through that. Differential equations is a lot like that. To some degree, it's a game of guessing. And the differential equations mathematicians who teach you the course will teach you some very educated guesses, some techniques to make educated guesses. The problem with differential equations often boils down to, okay, I got a solution, I plug it back in, it works. Is it the only solution, or is there some other solution out there, some other mathematical function I should be looking for that would also work? And so the idea of uniqueness is an important thing. But in the world of solving differential equations, and you've seen absolutely one so far this semester, because I showed you the wave equation for electromagnetic waves being derived from Maxwell's equations on the very first lecture of class, I guess. And I told you that was kind of to broaden your background, let you know what you got in store for you. Well, today we're going to come up with a second differential equation that's similar to that, that you have to not necessarily solve, because that's more the province of the next course you take, quantum mechanics, in this modern physics quantum mechanics sequence. But you should understand what we're doing. And I got to start what I always do when I'm ahead of the mathematicians, with some heresy. Anybody planning on majoring in math? It's okay if you do that. We like those guys too. They're all right. But here's the heresy about differential equations. It really is a guessing game. And then once you've guessed at a solution, you check it. If you can remember that about differential equations, you've learned a lot. Okay. They're going to show you techniques on how to make educated guesses. But at the end of the day, like that quadratic equation, you did a guess and check kind of thing, right? You guessed at some numbers and then you plugged it back into the quadratic equation and you saw if the number worked. If the number or numbers worked, you had solutions, right? And you all know for quadratic equations, there's two solutions. The problem with differential equations is there might be 3 or 4 different solutions, and or even more. In the case of Fourier series, if a cosine is a solution, well, then there's an infinite number of solutions who are also solutions to a differential equation. And so that's a lot of talk, but that's the thing to remember. We're going to presume solutions. We might guess at solutions. We're going to check by putting them back in. If they work, we're going to accept the fact that they're solutions, and we're probably not going to look for any others. That's a class for another day with a mathematics teacher, and hopefully they'll put it together. Now we're starting to talk about a field of physics called quantum mechanics now, and for the last 4.5 weeks, whatever we got left, that's pretty much what we're going to be doing. We'll look at various examples of quantum mechanical systems of particles in certain potential situations, potential as in potential energy situations, and we'll see how they're going to behave. And we've been talking about the hydrogen atom, right? And that's a potential energy system. You've got a positive charge at the middle. It creates a potential energy around it, and the electron in the hydrogen atom lives in that potential energy region, right? That's the deal. And so we're going to look at some other potentially bounded regions, and some of them are pretty fictitious. Like, can you imagine an electron at the end of a spring? We're not going to do that problem this time. I'll mention it. But so if I had a potential energy of a spring and I had an electron at the end of a spring, can you imagine the energy states that that spring might have? And that's a problem for quantum mechanics. We're going to go with something simpler. Let's say we had just a box and we put a quantum mechanical particle like an electron in that. What energy levels would it have? And these are all what one of my graduate school teachers used to call toy problems that physicists do, in order for them to understand more complicated problems that might arise in real, no kidding, atoms and molecules and systems like that. Okay, so quantum mechanics. Let's first of all talk about what it isn't, and then we'll talk about what it is. And so I'm going to start sharing with that as a preamble my PowerPoint slide. And hopefully you're seeing that. Do I see the border? It looks like I see a green border. Yep. Okay. And then I'm going to go to a slideshow view, which I don't often do, but it's risky with the annotation tool. But you're seeing a mass on a cart, and it's moving at some force, with some force being acted on it, and it's at some position. And I guess if I know that initial position, I know the mass, I know the forces that are being acted on it, can't I predict where that cart's going to be in the future? Classical mechanics has at its very root predictive nature. You can know where something is today and be able to figure out where it is tomorrow. That's how we got to the moon, right? We were able to figure out the mass, the forces, where something is right now. We knew a little bit about the domain of space between us and the moon, and we were able to get there, predict exactly where we'd land on the moon by applying the right forces at the right times, and do that. Quantum mechanics, it isn't that. Okay, it's an important idea. If you know where a particle is today because you just measured it, and maybe even you know its momentum to within the Heisenberg uncertainty principle anyway. So if you know its momentum, you know its mass and its velocity, you got no idea where it's going to be 2 seconds from now. It's not predictive. Quantum mechanics is not predictive. You can't look into the future and say, I know something today, I'll know where it is tomorrow. Doesn't work that way. All right, so what can you do though with quantum mechanics? Quantum mechanics, according to the generally accepted interpretation, because when this first came out, it was seen as pretty bizarre. Okay, and so a number of people tried to put spins on what quantum mechanics was all about. The predominant interpretation that won out was Niels Bohr and his was so-called Copenhagen interpretation, because of course Bohr is Danish, and so the people he worked with put this interpretation together. But you take the piece from de Broglie, these small particles, electrons, protons, neutrons, small bullets, they're waves, right? Well, there must be a wave function, and the wave function we give the symbol psi. It's a Greek Y. Where's my little, there it is. There's my little annotate pen tool. This thing right here, I got ahead of myself somehow. There it is. This thing right here, sorry about that. Well, I spoiled my surprise for you. The Copenhagen interpretation talks about this wave function. And on this slide, I make it a function of both a position, y, and time. That position could be x, could be z, it could also be y. We'll change those about depending on how things are oriented. And the point of this wave function is it describes the small particle, and it gives us the probability of finding the particle at a particular location at that instant in time. Okay, and so the probability, that's what P is standing for here, of finding the particle at a particular location y, and I guess you're within that small differential dy of that position dy, is this wave function squared times dy. Okay, so this wave function has a probability nature to it. And I've just drawn a hypothetical wave function squared here. So it looks like the most probable point to find it would be some point right there. And I made a little bit of, I'll call that dy, that segment right there. If I was to take then this area right here, okay, I guess I can find that area that would represent the actual probability of finding the particle there. That would allow me to get, I don't want to say probability because probability is the integrand. It would give me a number that would be representative of finding the particle at a particular point right there in that width right there. Okay, so that's what we're finding here. That's what these wave functions represent. The particles are waves, just as de Broglie, and if I do this math, that allows me to figure out a numeric value of finding the particle at a particular position. Now, that gives us an important point. Whatever this function is, this wave function, whatever math function it is, I don't know, maybe it's a cosine of, needs to be a function of y and t here, ky minus omega t. That's a possibility for a wave function. That would be a traveling wave, variables t and y, right? Whatever it is, if I integrate that thing over all space, well, then that probability, it has to be someplace. So if I integrate that thing from minus infinity to plus infinity, well, then I better be 100% certain I'm going to find it someplace. If the particle exists, when I do this math, I better get one. We call that normalization. And anytime you get a wave function, one of the very first things you have to do, if it's not given to you in that state, is to normalize it. And there are steps you have to learn to do in quantum mechanics. Even if you don't understand, frankly, what you're doing, the first step is you've got to normalize your wave functions. If they're not, then all this probability stuff doesn't work. And we'll talk more about Born and his interpretation of the probabilistic nature of this function psi. And I just throw this out as an example. There are many. We're going to use another one here in a bit, and that's the subject of the worksheet today, is a completely different function. Any questions on that? Hopefully as I go through this morning, you'll see more of what I'm talking about in terms of this wave function. But this is a probability right here. A probability of what? A probability that I'll find a particle at a particular point y at a particular time t. Not hearing any questions, so we'll move on. So how do you find psi? If it's a wave, there has to be some equation that governs the wave, just like when we talked about a one-dimensional wave on a string, or in the case of Maxwell's equations, we had an electric field, which was a traveling electromagnetic wave. If you want to find what the displacement of the wave on the string is, or what the electric field moving through space is, we had this thing called a wave equation. And in the case of an electromagnetic wave, it's not any velocity, it's the speed of light squared, and then it's the derivative of the electric field with respect to time. So it is not just a differential equation here, it's a multivariable differential equation, right? Because I've got second derivatives in position, and I got second derivatives in time in these equations, right? So it's not just an ordinary differential equation if it was only an equation that had x or t in it. This is known as a partial differential equation. And these two wave equations right here have governed a lot of classical physics. And so if we're now doing quantum mechanics, where we're trying to come up with this wave function, where the wave function represents a particle, it made sense to physicists in the 1920s or so that there must be a wave equation like one of these two guys that governed psi and told us how to find it. Well, the person who is responsible for coming up with that wave equation is a person named Schrodinger, Erwin Schrodinger. He goes off, literally, he's on like holiday, and he just wanted to go someplace, clear his head, work on this problem. And here is Schrodinger's wave equation. Okay. And I'm going to state it without proof, but I'm going to do an example here in a second that perhaps gives you a little bit of insight as to why Schrodinger's wave equation works. But it has similar characteristics to either the electromagnetic wave equation or the wave on a string, because there's a second derivative of something, whether it's the transverse displacement of a wave or an electric field. It's a second derivative of that thing, isn't it, in both cases? Okay, with some constants out front. You got constants here too, either 1 over the velocity squared or c squared. You can bring those to the other side of the equation. The time piece, completely different than your classical wave equations for a one-dimensional wave on a string or electromagnetic radiation, because in the classical case, it's a second derivative of whatever it is, transverse displacement or electric field with respect to time. In Schrodinger's equation, it's a first derivative. If you study differential equations, somebody will tell you that when you look at the first derivative of something in time, it's a rate of change in time. Sometimes it's referred to as a diffusion in time if something's actually moving. Okay, it tells you the rate at which it's moving. So it's a slightly different character to this differential equation. And then the last piece, which is completely different, is this term right here, where the wave solution, the wave function, okay, gets multiplied by a constant. And V here doesn't mean voltage, it means potential energy. And don't ask me why we don't stay with the symbol we had in Knight's book, U, potential energy, but it is the same thing, okay? V here is potential energy, which means U. It has units of joules, just like potential energy U does. But this is the odd thing. If the potential energy is multiplied by this wave function, well, it's in the differential equation. And that's completely absent from the classical case, right? There's nothing there added on to the classical wave equations. So Schrodinger's wave equation, it looks, because of this second derivative term, a lot like classical wave equations, but it's still different because this term is not in a classical wave equation. And this term here is a first derivative in time, not a second derivative in time. By the way, I said that this function right here, this wave function, could be a function of x or y or z. It could be all three at the same time, in which case right here, instead of 1 second derivative, you add up all three. And hopefully you realize what I've done there mathematically, if you've gotten that far in your multivariable calculus class, is I've really said it's a Laplacian in 3 dimensions, isn't it? And if you don't know what a Laplacian is, never mind. It's just 3 second derivatives added on. But hopefully you've seen that notation before. That's shorthand for writing that. And that's if you do happen to do a problem in 3 dimensions, and we will do 1 or 2 just to point them out. Actually, we'll do 2 problems like this. It just becomes a Laplacian. Okay. Now, I haven't said a word about the complex nature of this wave equation. You can see here I got an I right here. Okay. And sometimes in my solution, I might have an I as well. I is the square root of -1. It makes this the wave equation, Schrodinger's wave equation, and some of its solutions will often have a complex nature to them. They'll be complex numbers. And so one of the things I got to get out of the way right now is when we were talking about the probabilities on the previous slide, and I was squaring these wave functions, okay, we have to accept the fact that when we square a wave function that is potentially complex, the way you do that is you multiply the number not by itself, but by its complex conjugate. All right, and so what does that do? Let me give you an example of a complex number. Let's say a complex number is some constant a, that could be like 3, plus I times another complex number. Maybe that's 5. Okay. If I wanted to square this, what you don't do is multiply by itself, because the answer to that would be equal to, let's see, I guess it's a squared, and then I times I, if I is the square root of -1, that would be minus b squared. So it's a squared minus b squared. And then let's see, I'll have IAB and IAB, so plus 2IAB. Well, that's not what we want. That is not what we mean by this symbol where we put the absolute value sign and we say something is squared, okay? And so that's not the answer. What we say we do is we multiply by its complex conjugate. And so how do you get the complex conjugate of a complex number? Hopefully you've been told. If not, let me be the first. For the complex conjugate, you take any place you find an I and you put in minus I. And so when we do a square of a complex number to get this result right here, that's the math I have to do. All right, why do I do that? Well, look, I get a squared, right? And then I get I times I, that's -1 with a, that becomes b squared. And then look what happens to the cross term. It ain't there. Okay, so we want it to come out to be like this, a squared plus b squared. So this way is how I square the wave function in order to get a real number at the end. See, this multiplication left me with a complex number. That's not what I want. Okay, so the mathematicians have defined this symbol right here, absolute value signs and then squared, to mean take the wave function and multiply by its complex conjugate. Okay, everybody okay with that piece of math? Anybody never seen that piece of math before? All right, that's how we square a complex number. So we're good to go here. All right, I got to advance my slide now. Boom, boom. Okay, nothing else I want to say there. And so here's an example of a solution to Schrodinger's wave equation. And again, I'm favoring x here as my function. Could have been y, could have been z. I went with x. And so I got x right here, and I got time right there. And so I think you notice in this particular case, it breaks up pretty nicely into, and here's some notation for you, something that is only a factor of x and only a factor of time, a function of time, I should say, and a function of x. Okay, and the first thing I guess I want to do is well, what does this look like? What does this wave function look like? And so we'll plot these two things. We, just to make our life easy, we'll plot it t equal to 0, and so this exponential just becomes e to the 0, which is just 1. And so I plotted these things just to see, and we'll just kind of talk about what it means. I did it in Desmos. If you haven't found that program, a great little piece of software for plotting. There is the first thing, the wave function itself at t equals 0, right? It's just two decaying exponentials. The absolute value sign keeps the exponential symmetric for negative values of x. And then I went in Desmos and also plotted this guy right here, and at t equals 0. And so again, plotted with the absolute value. And all that does is throw a 2 up there in the exponent, right? Because when you square exponent, you just multiply them together. So that worked out really well. And I guess the question I'd ask you about this is where's the most probable place for whatever particle is being represented by this wave function? What's the most probable place for it to be located? And hopefully you'll look at this thing and go, well, based on what you said, right there at the origin is the most probable place it can be located. The second thing I would say is what's the probability of finding a particle out at, say, a real big value of x, like approaching infinity? What's the probability out here? And the answer is pretty small, approaching 0. And same thing at negative infinity. And if I wanted the probability at any place in between, well, I could just look right here and kind of figure out what that probability is by looking at the value of the square of the wave function. Now, here's the deal though. Is this thing normalized? If I take all values of x from minus infinity to plus infinity, and I find this area under the curve here for all those values of x, would it be 1? And my answer is probably not, since that's 1. It looks like it'd be much bigger than 1, okay? And so that would be our first step in this wave function, is to normalize it. And what that really means is determining what the value of this constant a was. When I plotted it in Desmos, I just made that constant a equal to 1. In point of fact, it's not. And that's going to be one of our problems on the worksheet today, is to normalize this wave function, square it, and integrate it from minus infinity to plus infinity, and figure out what that constant a must be in order that that integral be equal to 1. And then I'll know what to put in a plotting program like Desmos right there, wouldn't I? Because at x equal to 0, that's the value. It's not 1. It's got to be some other value. Okay, so that's the first worksheet problem we're going to be doing. The second thing I guess I got to talk about is, how do I know that this is a solution here? Sorry, I was going to just check in my next slide. How do I know this is a solution right here? I mean, I just proposed it. Is it? I'm saying it's a solution. Solution to what? To Schrodinger's wave equation. And so that takes us to the first worksheet problem that I'm going to do, where I'm just going to see, is this work? Is this a solution? Did I just pull this thing out someplace and just say, hey, here it is, slapped it on a piece of paper, or does it have any potential validity? And then what results from that? Okay, so I'm going to shift over, stop sharing this with you. First, I got to stop. Now it's not going to let me do that, is it? Stop sharing. Okay, and then maybe it'll let me end the slideshow. Yeah, I'll keep those, sure. And I'm going to slide on over to my iPad, where hopefully screen mirroring will take place. Good. And I'm going to do this first problem. So I just copied off the previous slide. There's Schrodinger's wave equation. Okay. And I also just copied my proposed wave function for some particle. I don't know what particle, maybe it's an electron. I have no idea what system it would be in, because one of the things that we have not specified here is what is the potential energy that is trapping this particle. So I haven't said anything about, great. Why is that happening? Oh, don't do that. Ignore it, go away. We're still in a, man, what happened there? It opened up Zoom on my iPad, because I do have that here. So let's go to what I want to go to, which is Notability. It closed Notability and opened Zoom. Still seeing the worksheet? I don't know what I hit, but back to where I was. I haven't said anything about this potential energy function, but we'll see what happens here. So how do I know if this thing I proposed is a solution? How do I know? Well, I guess I better take a first derivative of it. Okay, so let's see. What is the first derivative of psi, the wave function? And by the way, if you put a little foot and a head on it, it's a capital psi in Greek. And that's kind of important because we showed when you separate it out into only depending on a function only depending on x and only depending on time, we use the lowercase psi without the head and the foot. It's just a notation thing, but it is what people do. Okay, so in any event, let's take that derivative with respect to time. The great thing about complex numbers is if you take a derivative with respect to time, all that requires you to do is bring down an I omega. Complex numbers are great that way. Sorry, I was trying to erase right there. So all I have to do is bring down an I omega, and I've taken a time derivative. That's the great thing about complex exponentials. All right, so then it's just multiplied by the rest of the function, a times, let's see, a times e to the minus k times the absolute value of x, and e to the I omega t. It's like a time lag as I'm writing here, so I don't see the letters coming out. All right, that's going right in there. All right, that's the deal. All right, now we got to do a second derivative. Hopefully I gave myself enough room for that. Man, this pen is not doing well today. I'm going to try rotating here. Wish I had Sam's handwriting. You want to write this for me, Sam? Let's try that. See if it works a little better this way. And get the little, yeah, that looks like it's a little better, although I got to write smaller now. So let's see. I can't do a first, it's not doing all that well either this way. In any event, I can't do a second derivative in my head, just not that good. But remember, if I took the first derivative with respect to time, it just brought down the I omega. If I take a derivative of this thing with respect to x, it just brings down the minus k, doesn't it? And I suppose depending on whether x is positive or negative, if x is negative, it brings down a positive k. If x is positive, it brings down a negative k. So for now, you'll see it doesn't really matter. Let's just write plus or minus k, and then write the rest of the wave function, e to the minus kx times e to the I omega t. And let me jump out of here for just a quick second, because it's driving me nuts the way my iPad is performing here this morning. So let's close some things up just to make sure it is only working with that, and see if that improves my pen work here. All right, in any event, we'll slide that up a little bit, because now it's time to get the second derivative. And because that's what I was heading for, even though I wrote it right there and shouldn't have. I'm heading to the second derivative. This is going to drive me nuts. Come on, pen, start working today. Or maybe iPad, start working today.
I would close Notability and open it.
Yeah, reopen Notability. Let's give that a shot too.
No, sort of like close the application completely.
Yeah, I just made it go away, and then we'll reopen it. Let it reboot. See if that works a little better. All right, let's see. That looked a little better. All right, second derivative of psi, nah, it's still not great. With respect to x squared, let's see, I have to take a derivative of the thing right above, bringing down another value of plus or minus k. Bottom line, I get k squared times the amplitude, whatever a is, times e to the minus kx, that's a little better, times e to the I omega t. And that's what's going right there. So I've got the two pieces here put together, and let's see if it works. That's the whole point of differential equations. Is this going to work? And so I guess I've got I h bar, Planck's constant divided by 2 pi, times I omega times that a times, let's see, right here, e to the minus k times the absolute value of x times e to the I omega t. Okay, that's the left side of the equation. The question is that equal to, and that's really kind of a question right now, is that equal to h bar squared over 2m? Let me slide this up a little bit. And then I've got to put in this guy, k squared a e to the minus, and this was absolute value x here, k absolute value of x e to the I omega t. Okay, plus the potential energy times the wave function itself, right? Because that's the last term in my equation right there. And so let's write that in as well. And that was a e to the minus k x e to the I omega t, and that's an omega, just a lousy looking one. All right, so that, you know, we're back at now, did putting that answer, that wave function, into Schrodinger's wave equation solve it? And what resulted? All right, well, let's work with the left side. I times I minus h bar, because I times I, let's see, I times I is minus 1, so it's minus h bar omega. Let's see if there's some things we can cancel, like everything else. A seems to cancel because it's in every term, right? E to the I omega t, at the very least, I can factor that guy out of every term. E to the minus kx looks like it's in every term. And so what am I left with? Nothing on the left side. What am I left with on the right side? I'm left with h bar squared k squared.
Did you lose a negative sign there on
Where,
the
where?
h bar squared?
Right here, you mean?
Yeah.
You're right. Absolutely did. Dropped it. Yeah, I just didn't copy it correctly because I was messing with my pen. Yeah, he's referring to this negative sign right there. Thank you. Absolutely would have made me angry at the very end when it didn't come out the way I wanted. So yeah, there's a negative sign right there. Okay, and then divided by 2m. Okay, and then I guess cancel, cancel, cancel. The only other thing is left is V, the potential energy in joules. All right, a little bit of kind of review, I guess, from chapter 5. What is this right here? Well, remember, Planck's constant times the frequency is energy. And another way to write that, not in terms of frequency in hertz, but in terms of frequency radians per second, is h bar omega. So what I guess I have here is negative energy, which one might expect if this particle was somehow bound. We said its total energy is then negative. That's the definition of a bound system. Well, let's see, that's good. What is h bar squared k squared? Well, de Broglie said P is equal to h over lambda. So if I go 2 pi over 2 pi, which doesn't change it, h over 2 pi, that's h bar. 2 pi over lambda is k. So boy, this term right here sure looks like, and I'm not going to drop the negative sign here, minus momentum squared over 2m. And then I've got some potential energy, which I haven't said anything about. I don't know what it is. But here's the point. By showing this wave function is potentially a solution to Schrodinger's wave equation, I've given some justification to where Schrodinger came up with this thing. Because when I substitute this solution back in, what I find is that multiply everything by -1, the energy is equal to p squared over 2m. That's kinetic energy plus whatever the potential energy is potential energy was likely a negative thing in the first place. If you think about electrostatic potential energy, let me draw it real quick. Electrostatic potential energy is often written like this, and I'm going to write V. Out at infinity, it approaches zero, but then it becomes negative because we say things like, let's see, potential energy would be Coulomb's constant, Q1, Q2 over R. And if the two charges are different, this thing is intrinsically negative, isn't it? And that means attractive. Okay. And so it's very likely this guy would be negative too. So we have shown here that Schrodinger's wave equation for this particular wave function just boils down to the total energy, which came from the term on the very left, is equal to kinetic energy, which is the term with the second derivative with respect to x, plus the potential energy. And that's what Schrodinger worked out. And that's why his wave equation is valid. Questions on that? Questions
Yeah, I
on
had a
how to,
question.
yeah, go ahead.
I have a small question about the signs. I get what Sam was talking about. He was talking about uh, the negative sign on the right hand side, but I'm a little confused. If you can scroll down to one of the last lines, where does the negative sign on the left side of the equation come
Yeah,
from? I
okay.
just
Remember what I is. I is the square root of -1, right? And this I right here is also the square root of -1. And when I multiply them together, I get -1.
I
So
see.
yeah, here's a law, and that's the kind of reason why we're doing that out, because if you haven't spent a lot of time looking at complex numbers, anytime you have I dot I, it's equal to -1. Okay, and one of the
Got it.
i's is actually in Schrodinger's wave equation itself. The other was up in the exponent of my solution and had to be brought down when I took the derivative. And so that's where it came from. Okay. And as I said, the last piece is that the potential energy is very likely negative as well. Total energy equal to kinetic energy plus potential energy. That's all Schrodinger was trying to say. All right, I'm going to stop sharing that and go back to sharing my PowerPoint here and move on to the next guy. And I got a little over 5 minutes, so we'll get through the rest. And unfortunately, that means work for you. All right, hopefully you're seeing my PowerPoint again. I want to talk a little bit about the Copenhagen interpretation of quantum mechanics. And the thing to remember is that it has three pieces that go with it. So what is Schrodinger's wave equation? What are these wave functions? It includes the uncertainty principle of Heisenberg. Because if I've got these wave functions that perhaps give me the probability of finding a particle in a particular location, plus or minus, right, within dx of that location, the uncertainty principle of Heisenberg can be solved here because uncertainty in a position times an uncertainty in momentum has to be greater than or equal to h bar over 2. This method, this quantum mechanics, gives us a way to figure out what the uncertainty in x is. And we'll show how here in a couple of days. It also gives us a mechanism of finding out what the uncertainty in momentum is, and is completely consistent with what Heisenberg said about the product of those two things. Okay. It does talk about it does include the complementarity principle of Bohr. And remember, all that means is in the limit where something could either be considered as a wave in quantum mechanics or a particle in classical physics, where you're at a size or a speed where those two come together, you have to be able to have agreement, and you can either treat the thing as a wave for a particular phenomena that you're trying to look at, like position, or you can treat it as a particle, and those two have to be consistent in the right limiting domains. Okay. And then lastly, the statistical interpretation of Born, which is based on probabilities, which we've talked about a little bit. I have one more thing I want to add to that. Okay. This is a logical interpretation, or at least was at the time, and we continue to agree to that, with what Schrodinger's wave equation actually meant. Not even sure Schrodinger knew exactly what it would mean when he came up with his equation, but like a good theory, it has been proven through experimentation to be valid. If it wasn't, it wouldn't be much of a theory. It'd just be pretty math. Now, there is an issue about measurement, and I'm going to talk about that here in a second. But there's a little sticky problem, because if you make a measurement, well, you know where the thing is at that instant in time. And so you've got this wave function that might extend over all space, and you do a measurement and you know exactly where it is right this second. But once you stop making the measurement, what happens to the particle? And that's an interesting question in quantum mechanics and modern physics. So let's go on to talk a little bit about that. Okay, so the one little piece I guess I didn't mention, I talked about, okay, a wave function. When I'm finding that wave function squared, which is related to the probability, I've shifted over to x here, I'm always multiplying by the complex conjugate, such that this integrand right here, okay, once you do the integral, is a real number. I said over all space, it has to be equal to 1 if I do that integral. And what Born insisted, and turned out to be right, is if you want to know what the probability it is between 2 points, A and B here, well, that's no problem. Just integrate from x equal to A, the lower limit, out to x equal to B, what the upper limit is, and that'll tell you what the probability of finding the particle right in that shaded region would be. Okay, and so that's the third piece. I know that if I integrate over any position, the probability has to be 1 of finding the particle, and I guess this is the probability of finding it right here would be some numeric value obtained by doing this integral. Now, I want to give you a kind of a new word then. What are the units, perhaps? Wouldn't that be, in this case, a kind of a probability density? The units here have to be some number per meter, doesn't it? So that when you multiply by meters, you get a number, a ratio, a half. There's a probability of 0.2 that it be in this region. You need a number out there. And so this becomes a number once you've done the integral. All right, so that is what the units are of psi. And so I guess in this particular case, that's the unit of psi squared. The unit of psi must be 1 over square root meters, isn't it? In a one-dimensional problem. All right, so units, Born interpretation. I'm giving this thing a better name than just sort of like the probability. I'm calling this a probability density. So it's a probability per distance. And then once you do the integral, that is no kidding a numeric probability. And that's what Born said. All right, move on then. What about this measurement issue? So I've got this wave function here, but I make a measurement of the particle to figure out where it is, and I find it's right there at point C. What happens to the wave function? The interpretation that quantum mechanics accepts at this point is that for that instant in time, the wave function changes shape to that at the instant you make the measurement. And this is perhaps the most philosophically difficult part of quantum mechanics to understand. The experimenter here affects reality. By making a measurement, you actually change the wave function to where your measurement is. It has to be consistent with experimentation. As soon as you're done making your measurement, what happens? The other side of the arrow, the wave function goes back to what it was before you made the measurement. That is an integral portion of the Copenhagen interpretation of quantum mechanics. If you want to think about it in 2 dimensions, let's say you have a particle laying on like a slide going under a microscope, and this is sort of what the wave function looks like. Kind of looks like that one I started with, right? Where you have something that looks like this, okay, in one dimension, but that's going on in two dimensions. So swing that thing around and rotate it. Okay, that's where the particle could be. You can do a two-dimensional integral to figure out the probability of finding a particle in some area, right? When you make a measurement, wave function becomes a spike. As soon as you're done making the measurement, it goes back to being the original wave function. And if you can picture that in 3D, you're better than I am. The best I can do is picture it in two dimensions. All right, so that's the deal. Now that means something about this Copenhagen interpretation. Is it deterministic? Can I predict the future with it? Answer no. Okay, is the wave function real? Like, you know, a wave on a string, that's a real thing, right? That's a real wave function, not in quantum mechanics. These are complex numbers. You got eyes everywhere, and so you're going to have to learn to deal mathematically with complex numbers. Does it have hidden variables? The answer is no. Everything's out front. If you can work with it, it's there. Okay. There were some theories in the time that had variables that in nature that were hidden and weren't being revealed. Not in Schrodinger's wave equation, not in the Copenhagen interpretation. Do the wave functions collapse when you make a measurement? Yes. Philosophically, that means that is the observer influencing the reality? Yes. Observer's role is not passive to just look at what goes on. When you're in a lab doing an experiment on small things, you're affecting it. You're causal. Okay. Is it local? No. We're integrating from minus infinity to plus infinity. This is happening everywhere. Now I got a couple great quotes that I put here on this slide, which hopefully you appreciate if everything I've said today is like gobbledygook for you. Niels Bohr himself said, if you're not confused by quantum mechanics and quantum physics, you really don't understand it. And then Richard Feynman, who was the Caltech physicist who wrote the Feynman series lecture of physics, he's probably the most renowned physicist of the 1950s and 60s. He said he thinks you can safely say that nobody understands quantum mechanics. So he's right in there with Bohr. The guy whose textbook you'll very likely use when you take quantum mechanics at Washington College, if you take the course, I think it's not mandatory, but it's a great idea if you're planning on going on to graduate school in either chemistry or physics, frankly. What he says, what Griffith says, the author of this textbook, you might not understand it, but every competent physicist can do quantum mechanics. Okay, it's something that is a skill. You're able to go through the machinery of the mathematics, and then you look at the outcome afterwards, and you go, does that make sense or doesn't it? All right, and that's quantum mechanics in a nutshell. All right, unfortunately, because I had to talk about things and answer questions, there's two more problems left on the worksheet, and as Sam pointed out, they're hard, right? And that is what you have to do over the next, I guess you got homework due tonight. So very likely you're doing this tomorrow or Friday morning. You're going to have to take that same wave function that I looked at. And first of all, you have to normalize it. Okay. You've got to do this integral to figure out what that constant A is. That's a fairly easy integral, but you got to do it. Okay. And then the next thing you have to do, if I've got my problem right. Okay, so question two here. Did I go right from 0 to 2? Yeah, I sure did. Question 2 is to do that. And then the next question is, well, what's the probability when A and B here are 1 over K and minus 1 over K? So you got to do two integrals before Friday. I think you can handle it though, because you're all tough. Any questions on what you're doing in the worksheet by Friday? And we'll go over it right at the start of class. Last chance for questions. Remember, if you're not completely understanding it, it's day one. Lots of time.
Wait, so both the last worksheet and this worksheet are due on Friday.
That's right. We didn't talk about the Heisenberg thing. Yeah, we'll go over that on Friday as well.
Okay.
Yeah, we did that. Did everybody finish those problems last time?
I wasn't here. So
No, you weren't here. That's right. All right. I'll tell you what, the Heisenberg uncertainty ones, I'll give you time to work in class on Friday, but these two integrals you got to do before Friday's class. Good to go on that?
Wait, you said 2 integrals in this?
Yeah, so the worksheet, I want you to work before Friday's class, because watching people, you saw how ugly it was watching me take derivatives. I want you to work worksheet 24, the questions numbered 2 and 3 by Friday. We'll do the Heisenberg uncertainty principle problems in class on Friday, which is worksheet 23. We'll do those in class on Friday morning. So you don't have to do those before class. But
Do we get to go through it?
Yeah, we'll go
or
through 'em.
Should we just submit it?
for the 2 integrals for worksheet 24,
Yeah,
please submit 24. Just hang on to 23. We'll do those in class on Friday. All right. Yep, you'll do your
All right.
best. You can do 2 integrals. I know you can.
Yeah.
All right.
that'll be fine.
Have a great day.
All right.
We'll see you all on Friday. If there's any questions, I'll be hanging around here. I also have some of my 101 students that wanted office hours this afternoon. So I'll be on this Zoom call. I'm not going to shut it down for another half hour, 45 minutes or so.
Thank you.
You bet. You guys have a great day.
All right, thank you. Bye-bye.